Hello, everyone. Welcome to VMW at CAV 2020. Um, in fact, this is the sixth edition of VMW, which started at CAV back in 2015. We have a full program planned for all of you with 6 talks, a panel, an icebreaker, lots of opportunity for socializing. And we are also going to discuss the results of a community survey that we sent out that I believe many of you might have filled up. So we are going to spread out this program over 2 days and 4 sessions. Over 400 of you have registered for virtual VMW this year. Plus, we expect many live stream viewers who may or may not have registered. And we have also invited many friends of VMW, more senior people from the CAV community to join us. So we hope to see a lot of buzz around all the communication channels that we have set up this year. I would like to thank all the sponsors who made themselves available this year, even though we actually did not need to use any sponsorship this year because we are virtual and registration was free. But we still would like to express a big thanks to NSF that has been a constant continuing supporter of VMW. And also many thanks to Facebook and Galoa who generously supported VMW, agreed to support VMW this year and will also support VMW next year. So let me just reiterate the mission statement for this workshop. So we are all on the same page. The purpose of the verification mentoring workshop is to provide mentoring and career advice to early stage graduate students as well as late stage undergraduate students to attract them to pursue research careers in the area of computer aided verification, which is the focus of CAV. And the workshop always does and will always particularly encourage participation of women and underrepresented minorities. Let me also highlight that we expect you all to follow a code of conduct. We are committed to providing a harassment-free workshop experience for one and all. And we follow the standards for expected behavior and unacceptable behavior as defined in ACM's policy against harassment. I have linked it here on this slide, but you can just Google search it. You should just take a look at it and make sure you report any incidents of violations that you witness to us, any of us in the VMW committee or to the CAV chairs. So on to logistics for attending VMW virtually. Okay, there are, this looks like a handful, but I think all of you have seen these now multiple times in your welcome email in the Slack. So hopefully you have had some time to familiarize yourselves. So the schedule is available on the VMW website that I have linked here. We will use Slack for really announcements and any continuing discussions after talks, during breaks, after VMW and so on. That's where a lot of the buzz is going to be. So I encourage you all to be active and engaged on Slack. The Slack is essentially part of the official CAV Slack. We have a separate channel, the Verification Mentoring Workshop channel. So if you haven't joined this, please do. We will use a different platform for video chat to socialize. And that's Disco. It's a tool developed at UCSD. We will use it both during the breaks and after VMW for socialization. and also for an interactive activity that we have included in the program, the icebreaker today. And you should have received the invites already. So just make sure you are set up before the first break. As for the talks, during talks, we are not going to be doing our Q&A on Slack. We instead will be using Slido, which is a much more convenient and cleaner platform during the talks and during the panel. All the links are available on the Slack channel as well as the website. So you will notice that there are separate links that you need to use for different sessions. So just follow them as we go along. And make sure that you upvote questions by others that you would also like to know the answers to. We will be using looking at these upvotes to decide what questions to ask the speakers. We will be live streaming all talks just as we are doing right now on YouTube. Again, the links are available on Slack as well as the website. And recordings for almost all of the program will be available for viewing later in case you haven't been able to join us live. We hope you are all going to be active on social media. If you do post anything, please try to make sure this hashtag of VMW 2020 that I have included here. So with that, I would like to just remind you that this is the first ever virtual VMW. We have taken a lot of effort to make sure everything runs smoothly, but still there might be technical difficulties that we haven't thought about. So please be patient and do let us know if something is going wrong immediately, or please share your feedback later. We'll send out something after VMW. Let me just wrap up by introducing the VMW committee. We will all introduce ourselves. So I have had really an amazing committee this year with Raina, JeanBaptiste, and Arjun. We all will introduce ourselves, as will many of the speakers, hopefully, so that you get to know some of us and come and interact with us later. So I'll start. I have had a journey that has spanned multiple continents to my current position. So I grew up in Mumbai, and then I moved to the US, to UT Austin, in fact, where I did my grad school and got my PhD. And then I switched continents again and moved to Europe, to Vienna, where I did my postdoc at IST Austria. And then I again moved back to the US in 2016, where I started as an assistant professor at Purdue. That's where I am right now. Overall, in my research, I always try to ask this question: can we make it easier to write reliable programs using automated reasoning? And I have looked at different topics and applications and problems over the years, but right now my main focus is on problems such as program synthesis and verification, with the focus on distributed systems. I'll hand this over to Raina now.
Hello, I'm Raina Dimitrova, and my journey has a lot more stops than Rupsha's. So I started. I'm originally from Sofia, Bulgaria, where I completed my undergraduate studies. I started my research career in Germany at Saarland Universities, from where I obtained my MSc and PhD degrees. Then I moved just 70 kilometers away to do a couple of years of postdoc at Max Planck Institute for Software Systems. Then my next move was at a greater length. So I went to the US to do a postdoc at UT Austin. And shortly after that, I moved to the UK, where I took up a lecture position. So I started at the University of Leicester, and I'm currently at the University of Sheffield. And in a couple of months, I'm doing one more hope, this time again back to Germany, where I started to take up a tenure track faculty position at CISPO Helmholtz Center for Information Security. My research is focused on the specification, verification, and synthesis of reactive systems. So these are systems that interact continuously with their environment. And I'm particularly interested in applications to autonomous systems where I address the limitations faced by autonomous control due to imperfect sensing and stochastic disturbances. So I'm aiming to answer questions about what guarantees can we provide in uncertain environments and when the requirements that the system should satisfy are conflicting. So yeah, hope to talk to many of you at the course of VMW. Jean-Baptiste?
Yeah. Hi, my name is JeanBaptiste Janna. I also spent maybe not quite as much as Rupak, but had also several continents. So I grew up and did my undergrad in France and at École Polytechnique, and then in 2007 I moved to Cornell, actually initially to do a master's of engineering in computer science. So just a one-year program, and then during that time I fell in love with research and switched to the PhD program, got my PhD from Cornell in 2013, and then moved to Carnegie Mellon to do a postdoc in Pittsburgh. Spent 2 years in Pittsburgh at Carnegie Mellon. Then went to the Bay Area and worked as a researcher for Samsung Research for a couple of years until 2017. And then for the last 3 years, I've been an assistant professor at the University of Michigan in Ann Arbor. One thing that is unusual is that I'm not in the computer science department at the University of Michigan, but rather I'm in the Department of Aerospace Engineering. And the reason for that is because my work is on making sure that cars, but especially airplanes, are safe and their software is safe. Airplanes have more and more software on board, and how do we make sure that there is no bugs that are going to cause safety issues? As you see, moving around, I've taken lots of planes and lots of cars. I actually drove across the country both times, going to the West Coast and coming back. But so I really have vested interest in making sure those vehicles are safe. So not only want them to make sure they're safe, but also how do we verify them, how to certify the onboard software.
Hello, I'm Arjun Radhakrishnan. So I'm, I think, the last organizer in this list. So unlike my colleagues who move all over the place, I tend to move westward, like slowly at a rate about 1,000 miles per year. So I started out at, I'm originally from Bangalore, but I moved to Bombay for my undergrad, then moved to Vienna to do a PhD. Did a postdoc at Philadelphia, and now I'm in Seattle and I'm working at Microsoft. And my research mainly focuses on the question of, can I get away without programming? So can computers help me program or develop systems? And in this space, I have looked at various different kinds of systems. So for example, concurrent programs, or how to write efficient programs, or currently I'm looking at a lot of systems which handle noisy data. So you can ask me anything about this on either the Slack or Slido.
So with that, we will hand over this session to Raina, who will be chairing this session.
Welcome to the first session of this year's VMW. I would like to remind you that you can ask questions on the Slido. So the Slido links are in the program for each of the talks. And now I would like to introduce our first speaker, who is Rajeev Alur, who is a professor at the University of Pennsylvania. His research is focused on formal methods for system design and spans cyber-physical systems, programming languages, and theoretical computer science. He has received numerous prestigious awards for his research. I just would like to mention that he has received the first CAV award in 2008 for his fundamental contributions to the verification of real-time systems. And I would also like to mention that his seminal paper, A Theory of Timed Automata, has, as of today, received 8,685 citations. So without delay, I would now like to welcome Rajeev, who will give us a brief introduction on the field of computer-aided verification.
Thank you, Raina. Can you all see my screen? And does it look okay?
Yes.
Okay, great. So yeah, thank you for inviting me to give this talk. So what I'm going to do is to give a brief introduction to the field. So, and this would maybe useful for students who are thinking about joining CAV. So it will be CAV-centered introduction to the field of verification. And it's good to know a little bit of history and what motivated people to look at these problems and how the field evolved. And I'll also tell you about how I got involved in CAV. Of course, it's a big field, so I cannot do justice to all the trends in the field, but so I'll look at some selected topics and tell you the story of CAV. Yeah. And feel free to ask me questions. So I guess on Slido. So Raina, if you see any questions, feel just interrupt me, and I'll be happy to answer them as we go along. So the verification is an old topic, and actually one of the early papers and very influential papers is by Tony Hoare, which was published in Communications of the ACM in 1969. And the title is an axiomatic basis for computer programming. So I have the slide has the abstract of the paper. And the crux of the abstract and the paper is that we should be thinking about properties of programs with the same mathematical rigor as mathematicians think about mathematical theorems. So we need a precise semantics for what the program does. We need a specification for what the program is supposed to do. And then we need a mathematical proof that the program actually implements its specification. And well, as the last sentence of the abstract says, finalists argued that important advantage, both theoretical and practical, may follow from a pursuance of these topics. Right? So that's been the goal of CAV, to show that by following this agenda, you can actually have practical benefits. But this turns out to be actually a very challenging problem. And the writing...
Excuse me, Rajeev. I think you have the wrong screen shared. We cannot see your slides moving, and they're not full screen.
Yes.
Oh, I have the... So, okay, what's the...
Okay. I guess you can stop sharing and share. Okay, I think now we can, but it's not full screen. Yeah.
Okay, so I think the, how about, no, this, no, this causes problems, right? Yeah, okay. Yeah, I think this is kind of a challenge with Zoom. How about now?
Yeah, this is good.
Yes, yes.
Okay, thanks. Yes. Okay, so so writing proofs of programs. So this was kind of the original motivation for verification, but writing proofs turns out to be pretty challenging. So here what I have on this slide is a program to sort an array. So it's a very classical program, selection sort, with two nested loops. And what we would like to show is when this program terminates, the array is sorted, which means for every k, the kth element is less than or equal to k plus 1th element. Now, to show that this condition holds at the end of the program, we need to come up with a modular proof. And this basically amounts to finding loop invariants which capture the logic of what the program is doing in a concise way. So in particular, if we look at the outer loop, then after I iterations of this loop, the way this program works is that the first I elements will be sorted. And furthermore, these first I elements will be less than or equal to any element after the I elements. So we need to specify this in a logically precise statement, and that's this invariant. And exactly what this invariant says is not super relevant for my talk. But if we follow the traditional methods for proving correctness of programs, well as introduced by Hoare, we would have to come up with invariants of these sorts. Well, this program has two loops, and if for the inside loop, then we have to come up with a precise characterization of how much progress the program has made if we have executed I iterations of the outer loop and j iterations of the inner loop. As you can see, getting these conditions right is pretty challenging. So as a result of this, after Tony Hoare published this grand vision in 1969, people were trying to show that program verification can be practical, but turned out to be much harder than we could have hoped for. And this is another influential paper, and now from 1979, also published in Communications of the ACM. And well, the title says Social Processes and Proofs of Theorems and Programs, but we could, it might as well have been titled Program Verification Declared Dead. And so basically it argues that this is not a promising agenda, and as this abstract says, there are a lot of challenges. For example, what happens if the specification changes, and of course it's hard to get the specification right in the first place itself. But furthermore, it argues that even if you were to produce this proof, would it actually convince people that this program is correct? Because there could be bugs in the proofs also. So it's kind of questioning this whole objective. Fortunately, even though program verification turns out to be hard, there is a related question, and which is as useful as verification itself. And this is about specifications. And so what's a specification? Well, I would encourage you to read this beautiful little article by Leslie Lamport, which is actually fairly recent, in Communications of the ACM in 2015, after he won the Turing Award. And it's titled, Who Builds a House Without Drawing Blueprints? And the let me just highlight a few things here, that it says that a blueprint for a program is called a specification, and an architect's blueprint is a useful metaphor for software specification. And so that's a very good analogy. And then he goes on to say that the specifications, the need for specifications follows from two observations. The first is that it's a good idea to think about what we are going to do before doing it. well, makes perfect sense. And the second observation is that to write a good program, we need to think above the code level. So we shouldn't start coding, but rather first think in more abstract terms. And finally, here is another excerpt from this article where it says that the main reason for writing a formal specification is to apply tools to check it, right? And this is actually where the CAV comes in, that we want to, we should be writing specifications, but we should also be developing tools to check it. But how do we bridge this gap between, the fact that for programs, specifications could be very complex, and getting a complete specification could be very challenging. And that's where the focus on the focus on verification tools comes in. And so ideally what we would like is to have a verification tool which takes a software or a model as an input, a correctness specification as another input, and produces a proof that the software satisfies the specification, or if not, produces an evidence that the software is incorrect. So two things to note about this, that the correctness is formalized as a mathematical claim, so as envisioned by Hoare even in the early work on verification. And its correctness is always with respect to a specification, but the specification doesn't have to be complete. It could just be one aspect of the program. Now to build, and then our focus is going to be this middle box, the verifier. But of course, there are fundamental challenges to build this box, right? So the one is the impossibility result of the automated verifier, that it's following the work of Church and Turing, this having a completely automated tool which does this is not possible. It's mathematically impossible. And even if we narrow down the problem, scale it down to where the model is only of a particular kind, the specification is also of a restricted form, maybe the question is decidable, but the complexity, computational complexity is very high. So that actually brings us to the first research thread in CAV that I want to talk about, which started in the 1980s after this gloom and doom about whether formal verification can it be made practical at all. And so what people did was they narrowed down their focus to particular kinds of problems, and what we call finite state models or finite state protocols. And network protocols is a good example of it. So maybe you have a communication protocol between a sender and a receiver, and you want to show that this protocol would never deadlock, or every request would be acknowledged. Or maybe this receiver has a buffer of a specific size, and we want to know, can it overflow in the worst case? Right? So for such systems, you can abstract away from the specific contents of the messages and focus on just the control skeleton of sender and receiver. And then both sender and receiver can be viewed as finite state processes, which are communicating, and there are a lot of interesting issues and exactly what's the communication model. Well, if a sender sends a message, is it synchronizing with the receiver, or is the communication asynchronous? How do we express properties such as every request is eventually acknowledged? And there are temporal logics where you can specify such properties very succinctly, and there is an elegant theory underlying that. And then people build tools such as Spin and Murphy. So Spin is a model checker that was built in Bell Labs in 1980s. And part of my, on my slide, you can see this screen dump. Actually, this is from a very early version of Spin, where what you see are like these two processes. As you can see, each process has a finite number of states. And what the tool would do is take a product of these processes and explore it in an efficient manner to reveal bugs. So here is sort of the core problem or the core technical challenge in doing this. So if you think about the analysis of finite state protocols, what we want to prove is that all executions of the protocol satisfy a correctness property. Well, since the protocol is finite state, we can think of just a large finite graph where a vertex corresponds to a state of all the processes that are participating in the protocol. An edge corresponds to one transition of the system, which could be a step by one of the processes, or it could be a synchronization between two of them. And what we are, if we are looking for, can the protocol reach an unsafe or a bad state, it's basically a graph reachability problem. But compared to traditional graph problems, the graph is not given explicitly as an input to us. In fact, the key challenge for the verification tool is to build this graph from the description of the protocol in an incremental manner, only as needed, and guided by the property that we are trying to prove, and while trying to limit the number of states that we visit, or trying to reduce the size of the graph that needs to be explored to reveal errors, right? So we call this problem state space explosion, where the size of the graph explodes exponentially with the number of bits needed to encode a single state. And in the 80s and 90s, a lot of activity was focused on how to do this efficiently by exploiting structures such as symmetry. So maybe there are multiple processes participating in the protocol, but maybe they all behave similarly, in which case we can exploit the fact that parts of the graph look very symmetric, and we don't have to explore them again and again to find an error.
We have a question from Slido, just excuse me.
Yeah.
So the question is whether you could please elaborate on the counter arguments to the paper program verification declared dead.
Yes, I'm coming to that. Yeah, good question right here. So so I'll talk about it in a minute, but the short question is this focus on finite state protocols, right? Where now all the activity became about algorithmic tools and how to battle the state space explosion. And in fact, so if you look at this previous slide, the specifications here, is there a deadlock? So that's not actually a complete specification of the system, right? So going back to the sorting question, right, where the fact that at the end the array is sorted, and to prove that, there is really no way around that than finding this loop invariance, which capture what happens when after say I executions of the loop. Well, the fact, if you think about a specification, like is there a deadlock in a communicating protocol, that's not a complete specification, it's just very partial. But finding a deadlock could actually be very useful. It could be an error that a designer has missed. And to reveal this error, what we have to do is to do this exploration in this large graph, right? So this switch to partial specifications, algorithmic techniques, and purely automated methods, where the programmer doesn't really have to come up with a complex specification of the complete functionality of the program. That was a key to, I guess, overcome to some extent the objections raised in, say, this DeMillo-Lipton paper.
So there is another question regarding specifications, and somebody is asking if it's possible to write specifications for existing programs as opposed to writing specifications before writing code.
Yeah, so ideally we should be writing specifications before code. And in fact, I completely agree with Lamport, who said that So going back to the slides, who builds a house without drawing blueprints? Well, and programmers shouldn't be writing code without writing specifications. But the fact of the matter is that, of course, programmers do that. And so we could, so if I want to develop a new system, we should be writing specifications. But let's say I'm given an existing piece of software, right? I could go the CAV way, which is kind of a, it's a practical approach and it focuses on very certain kinds of errors. So I could try to find null dereferencing errors in existing C code without debating whether, should a language have pointers or not? Should we be using C or not? Is C a good language? How do we write specifications about C? Which are all interesting questions. But if we just focus on the analysis question, I could say, well, there's a lot of C code out there, and I could just focus on a very specific kind of error in C program and try to develop tools to find those kinds of errors. But in the 1980s, the switch to finite state protocols is actually what revived verification. And one of the success stories from this era, more than the verification tools, I would say temporal logic, right? So linear temporal logic, which originated actually about 100 years ago in philosophy by a philosopher known as Prior. And later in 1970s, Amir Pnoeli adapted it to specify requirements of reactive programs. So programs like communication protocols and operating systems that interact with the outside world in an ongoing manner. And it's a beautiful notation where you can express properties like always, if request, then eventually response. And it just like regular expressions and the relational algebra and SQL, temporal logic has now become kind of a standard specification language. And even if we don't use it to verify, we can use it in many different contexts, for example, in planning, in robotics, or in hardware, where the programmer embeds these temporal logic specifications in a Verilog or VHDL code, and then the simulator checks while simulating the code that the temporal logic specification is met. And a particular variant of temporal logic, which has proved to be quite useful, is this language called property specification language. So what you see at the top of this slide is the snippet, which is a PSL specification, which is some extension of temporal logic for. So with this, this emphasis on finite state protocol analysis and temporal logic actually convinced some people, and these actually the 4 people who founded CAB. Ed Clark was a professor at CMU. Bob Kershan, he was at Bell Labs. Amir Pnoeli, who was a professor at Weizmann Institute of Technology, and Joseph Sefakis, who was the director of a research lab at Grenoble in France. So they said that even though, maybe this idea of program verification is not gaining traction, but this focus on finite state protocols and temporal logic and finding bugs in distributed concurrent systems using state space exploration techniques is a topic that's worth exploring. And that led to foundation of the CAB conference. And it was first held in 1989 in Grenoble. So this year, you are attending the 32nd edition. And here is the introduction to the to the conference, the first conference. Actually, it was a workshop. At that time, it was workshop. It was very small, like maybe 50, 60 people. And the proceedings were published by Springer. And even now, that tradition continues and it's published as a volume of lecture notes in computer science. Well, this was in 1989. It was 407th issue. I don't know what it is. It's probably, I guess, more than 10,000 issues. But yeah, if we look at this, it says its first workshop entirely devoted to the verification of finite state systems. And then I have, the keywords here I've highlighted in red. These were the topics of interest at that time: process algebras, automata, and logics. So people were debating about what's the right notation, even to specify these finite state concurrent protocols, what's a good notation, right? And a lot of theoretical work in terms of understanding expressiveness, understanding complexity of various decision problems, focused on automata, logics. And then the application areas were hardware design, communication protocols, real-time systems. Actually, Rupsha had asked me to show this slide, about my history, but I have a variation. So I'm going to tell you about how I got involved in CAB. So at this time, well, so we are in 1989. So at that time, I was a PhD student at Stanford University. And so one of the papers in this first CAB is Timing Assumptions and Verification of Finite State Concurrent Systems by David Dill, who was a professor at Stanford. And at that time, I was working with Zohar Manna, focused more on real-time temporal logics. But I looked at this paper and thought, wow, this is very interesting. And I talked with Dave, and then he became my co-advisor. And actually, this paper was really the catalyst for my thesis. And as Rupsha mentioned, so my thesis was on timed automata, and it turned out to be quite influential. And we are grateful and fortunate that we were awarded the first CAB award in 2008 for that work. But yeah, so following that year, then so I attended the second CAB, which was held in 1990, and I've attended lots and lots of CABs. It's a pity that we can't meet in person this year, but usually I love to go to CAB and meet all the colleagues, but also new students and all the new researchers. And hopefully you will also find inspiration for your thesis in the papers that are being presented in CAB this year. And so Bob Kershan, who was actually one of the steering committee members, so he liked my work on timing verification, and so he hired me in Bell Labs. So I joined Bell Labs in 1991 after finishing my thesis, and then I worked with him, and we implemented some of these ideas in the tools at Bell Labs. And so my first CAB paper was actually in 1992, which was titled Timing Verification by Successive Approximations. Right? And as I said, I've been involved in CAB in many roles over the years, and I was co-chair for CAB in 96 as well as in 2004. Okay, so going back to research trends. So in 1980s, these were at the beginning of CAB, these were mainly about efficient ways for exploring large state spaces and coming up with different heuristics so that even though the number of states of a protocol grows exponentially, how to explore it in an efficient way so that bugs are revealed without paying that exponential price, right? Or in a typical case, not pay that exponential price. But one key breakthrough in terms of how to represent the state space. So instead of listing states one by one, trying to represent them symbolically using constraints. And this idea gained a lot of traction in a subfield of CAB called symbolic model checking. And it amounts basically to constraint-based analysis of Boolean systems. And a model checker called SMV was developed by Ken Macmillan. And actually, Ken, I think, is going to give a talk in the verification mentoring workshop. And I haven't talked to him, but his title suggests that he's going to talk about different ways of addressing scalability. So I suspect he will talk about symbolic model checking. So I'm going to skip the next few slides because we also want to, I want to finish on time and leave some time for questions. So, but you're welcome to look at the slides which are about the symbolic teachability. And this actually became very popular in hardware verification. And but yeah, let me tell you about this context that in every phase of CAV, the catalyst to success has come from industry. So in 1994, Intel had a bug in their Pentium design. It's known as FDIV. So it was actually an error in floating point computation. And so even though Intel had spent a lot of time in simulation and testing of their designs, this bug went undetected. And this, of course, caused them a lot of problems. And well, to put a specific cost metric on it, well, it cost them $500 million. And at the same time, in CAV, symbolic model checking was advocated as a way of finding hard-to-find bugs in hardware designs. So they got very interested. And then, particularly in the late 90s, Intel built this big verification groups where they hired like hundreds of PhDs with expertise in formal verification. And even today, this remains a vibrant area. So actually, OSCE is a company that they don't, I mean, they sell tools, but they also sell verification consultants, and it's one of the sponsors of this year's CAV. And I hope some of the OSCE people are around and you can ask them about their experiences. And in hardware design automation companies like Cadence and Synopsys, complementing simulation and testing tools with some form of model checking remains a research thread even today. But now switching gears, let me talk a bit about the next phase of CAV, which actually started the stimulus to this research came from Microsoft. So I think I'm sure many of you use Windows, and these days Windows is actually fairly reliable. I mean, it does crash, but those of us who were around in the 90s, it would crash very frequently. I mean, it would have crashed sometime during the course of my talk, for example, which is no longer the case. So the challenge there was, how do we get Windows software to be correct? Well, so going back to this criticism that, okay, well, full program verification is actually impossible. And that's definitely true for Windows software, which is millions of lines of code. But when they analyzed the source of the crashes, it was mostly due to the third-party device drivers. So for example, someone would come up with some idea for smart camera, and the company would develop a great smart camera, but then to download the pictures onto your laptop, you need to connect the camera to the laptop. And the device driver code has to, which is written by the people working at the camera company and who are not sophisticated software developers like the ones that Microsoft hires to develop Windows software, they would make mistakes, even though the kinds of mistakes that typically cause crashes, such as you acquire a lock and don't release it, have been clearly spelled out in this Windows driver development kit. So Microsoft said, can we use some analysis techniques to reveal these kinds of bugs? So here the specification is given. So this problem of how do I write specifications of complex systems is punted. I'm again going to look for a very specific kind of bug, which is the lock. Anyone who is interacting with the OS has to follow a particular locking discipline. Right? It's more like a rule that the code should follow. Right? And of course, just following this rule doesn't make it correct. But violating this rule is clearly a bug and has to be avoided. And of course, an expert programmer is unlikely to make this mistake. But if it's written by these programmers whose expertise is not mainly programming, like they could be developing some engineered products, it could easily happen. So what Microsoft was interested in a tool that would certify this code written by other people for these kinds of errors. And the technique which was developed in the CAV community and has now we call it model checking code or software model checking, and started around 2000s, is basically this, that in the first phase from this C code that you see on the screen, you construct a finite state abstraction. So in the finite state analysis, we saw that if the model is a finite state thing, then maybe things like symbolic model checking or exhaustive exploration of reachable states with lots of heuristics built in to battle the complexity can be very fruitful, right? So here the idea was to repurpose those techniques, but in the context of actual C code. And the way you bridge this gap is by first translating the C code to some bare skeleton, which is finite state. So instead of, for example, keeping track of integer valued variables such as n packets old and n packets, we can just keep a Boolean variable which keeps track of whether these two integers are equal or not. And that's done using a technique called abstraction, predicate abstraction. And what we want is that given the C code, we build this abstract model and check this abstract model for violations of correctness requirements. If the abstract model is correct, we are done. This analysis could reveal an actual problem with the code. And if not, we have to go and refine the abstract model. So a lot of work on how to do this refinement automatically and effectively. And if you look at CAV papers in the 2000s, there's lots and lots of work on software model checking. So the moment you start talking about code, well, there are lots of issues to deal with procedures, pointers, objects, inheritance, and so on. And a number of tools have been developed. And a nice success story from this era is this tool called SLAM. So SLAM, it started in the CAV community, and this was for software model checking, but it was integrated in Windows development, and it's under the name Static Device Verifier. And here is a quote from Bill Gates, which says that things like even software verification, this has been the holy grail of computer science for many decades, but now in some very key areas, for example, driver verification, we are building tools that can do actual proofs about the software and how it works in order to guarantee the reliability. So this is a clear success story where a mainstream software development company is using verification technology. Again, not meeting this grand dream of proving software correct, but rather with a focused approach, right? So basically, the short summary is that we can't use verification as a hammer, but more as a, like a precision instrument. So another very exciting research trend in CAV has to do with constraint solvers. Right? So the basic problem here is propositional satisfiability. So if I give you a formula over propositional variables, finding whether the formula is satisfiable, it's a canonical NP-hard problem. And anyone who has studied computer science knows that, well, this is not a, showing a problem to be NP-hard suggests that the problem is intractable. But thanks to sustained effort by the CAV community, now we are at a stage where the SAT solvers have progressed to an extent where formulas with thousands of variables and millions of clauses can be solved. And here I have a timeline which is not quite up to date, but the first SAT solver was apparently written by Quine in 1952, and it could, I guess it did exponential search and could handle 10 variables. And over the years, there were lots of interesting ideas. For example, this idea of using binary decision diagrams, which is used in symbolic model checking, was around late 80s. But then in late 90s, early 2000s, a lot of interesting ideas. For example, in this SAT solver called Z-Shaft came around, and the progress keeps happening. And so right now we can handle constraints with 100,000 variables. So in the end, the checking whether some verification condition holds or not is converted into some constraint solving problem. And a more fancier version of SAT is what we call Satisfiability Modular Theories, or SMT. So many of you who have taken a course on verification would know about this, but for those to whom this seems like a strange buzzword that they don't know what it's about, I have like one slide explanation. So instead of solving constraints over just Boolean variables, imagine you have to solve constraints over a mix of variables, say Boolean variables and integer variables. And the constraints could be, well, maybe linear constraints over integer variables, like say 2x plus 3y less than 5, and maybe a Boolean combination of these constraints. So how do we check satisfiability of such constraints? Right? So this is really a problem of finding a model for a logical formula, except the interpretation for symbols like addition and so on is fixed. So that's why it's called modular theories, where the interpretation of some of the symbols is fixed. Right? And there has been a tremendous progress in these SMT solvers. And so starting in 2005, an annual competition was started, and there is a standardized interchange format, and lots of tools have been built. For example, the Z3, CVC4, these are some of the state-of-the-art SMT solvers, and a lot of verification tools, testing tools, more and more planning tools, and many problems arising in different parts of computer science now use these SMT solvers. And the last research trend that I want to tell you a bit about is looking at safety-critical embedded control software. So here is an example of a system where you have a pacemaker, and a pacemaker has two leads, one in the ventricle and one in the atrium, and it's monitoring the timing signal that it gets from these two leads. And it needs to detect whether this timing pattern looks acceptable, or maybe it's a symptom of some arrhythmia condition, right? But in the end, it's going to be implemented as a piece of code. And so how do we verify that this piece of code actually satisfies the specification published by FDA? And can we use verification techniques to certify this? So this has led to activity in cyber-physical systems. So cyber-physical, because it's software interacting with the physical world. And we have developed a number of models. So I told you a bit about the work on time automata that I had did. But there is work on hybrid automata, so extending automata with differential equations. And this has led to a very fruitful collaboration between researchers in formal methods and researchers in control theory, resulting in a number of verification tools and applications to safety of collision avoidance protocols. But more than, again, verification, actually one success story here is this whole idea of more model-based design, right? So here is one where actually you first think what you want to do before writing code is more acceptable and more in tune with industrial practice. So MathWorks actually sells these model-based design tools, and they use tools like Stateflow, Simulink. And in the 90s, they were actually averse to making the semantics of their models very formal. They were averse to having correctness specifications embedded in these models, but that has changed. So if you look at the MathWorks products today, then in fact they do admit very formal notations like hybrid automata as one of the Simulink domains. And they have a tool called Simulink Design Verifier, which allows you to specify properties rigorously and applies tools from model-based testing and static analysis to check that the model satisfies the property before converting the model into executable code. So I'm, in closing, well, first I want to say that I had limited time, so I covered a few of the research prints. This is not meant to be an exhaustive list, but something that should give you an idea of what the field is about. There have been lots of success stories, but if you look at any success story, essentially it goes into phases. So the first phase is you have some initial demonstration that there is a good match between capability of a research prototype and a real world need. So for example, the SMV model checker is useful to find some kind of bug in a industrial scale cache coherence protocol, and then a decade of research to make the method scalable, to integrate it into industrial practice, and so that the tools are applicable to problems of real world interest. And there are lots of exciting research opportunities, and I hope that you attend the CAB with an eye towards that. And let me just mention one, mainly because I'm working on it currently. So this is, can we develop verification techniques for safe autonomy? Right? So I hope you can see this video. So this is actually a car which is called F110 racing car, and it's built in the Precise lab at Penn by my colleagues. And on board you have this LiDAR, and so you are getting measurements of this LiDAR. And in this particular experiment, what we did was we trained the controller using reinforcement learning algorithms, and it's implemented as a neural network. So the problem here is that from the LiDAR rates, we want to decide what should be the speed and the steering inputs to the control inputs of speed and steering, right? And since there is so much activity and excitement about applying machine learning techniques in all kinds of domains, here it's natural to try to see if neural networks can improve the performance, right? Of course, if I implement something as a neural network, the question is, particularly in the safety critical applications, can we trust that controller? So this safe autonomy is an area where you want to look at autonomous systems, which could be driverless cars, or this is kind of a toy version of that, but where some key component is implemented is trained from data and implemented as something like a neural network controller. And now, so we have this problem where we have a plant, we have a well-defined model of the plant, and we have this neural network-based controller. We have a clear specification. Well, the car shouldn't collide, right? It should have, and it should follow the reference trajectory, and it should be stable. So the specifications are clear. So can we develop analysis techniques to prove this, right? And it's a new problem, lots of opportunities to make progress. And in this year's CAV, also last year's CAV, there are some very interesting papers on how to go about doing that. So thank you, and we can use the remaining time to take more questions.
Thank you very much for the great survey of the area. We have so far plenty of questions on Slido, and we have sufficient time for some of them. So One of the questions on Slido, which is currently on the top, is one of the major concerns in model-based verification is how to verify that the model actually corresponds to the real system that we are verifying. And the question is whether there is any progress on that.
Excellent question. So in fact, since I'm right on this slide, this is something we are currently struggling with. So how do you build a model of the LiDAR, right? This is because there is a lot of uncertainty, and so how to build a good model of the, what you get back from LiDAR, which it's a real problem, and particularly in the control setting, people call this sim to real gap. So maybe you have a simulation model, and then you have a real world system, and can you bridge this model, right? There is of course no definitive answer to your question. There's a lot of research, but in the end, we have to understand that models are not going to be perfect. But if the models turn out to be useful to design your system and debug the system, then that's good enough.
Thank you. There is one question which is on the kind of more like career orientation side. So the question is, what are the verification tools that need consultants? You mentioned Jasper. Are there any other examples?
Oh, yeah. So what I meant was the business model of companies like OSCE and Jasper is that they consult with, a company that's designing hardware. Well, if you look at a company like Intel, then they would have an in-house verification team. And so if they think a particular piece of design is complex and they needs application of formal verification tools, they will use the in-house people. But maybe someone is coming up with a new design for, let's say, a memory controller or something like that, right? And such a company may not have in-house verification expertise. So what they do is they hire Jasper or OSCE, and what these companies will do is they will provide, they will look at the problem, see which tool is most relevant, and then for some of these tools you have to pay a lot of money to get a license, and yeah, help with that. Right? So it's not like these companies don't have their own tools. They work as a bridge between industries that need verification, and then either academic or tool vendors who are producing verification tools. In the end, I think the applying any verification tool it's not automated, even though sometimes we say that model checking is it's automated. It's not really. I think you have to figure out what's the level of abstraction at which the problem needs to be modeled and how to use the tool. And so a lot of expertise is needed for that. And you can sell expertise and not really tools.
Thank you. I think we have time maybe for one or two more questions. So there is one question asking how to be confident, that it relates to what you were just saying. So how to be confident about the verifier's correctness?
Oh, can we be confident about verifier's correctness? So
Yes.
So there is, of course, this trend, which I did not mention, is to build to build more pure verifiers. So for example, in a proof system like Coq, and where you could try to build a fully verified system. If you look at a model checking tool, it itself is a large piece of software, and it could be making errors. And there is so I would say there's no good answer to your question. I mean, like any other tools, the tools themselves could have errors, and the designer in the end has to look at the error trace produced by the tool and see if this is something that they trust. Is this something that needs fixing? But that applies to all kinds of tools. In fact, even in systems that have been used, if you look at GitHub repos or something, you will see a lot of bug reports, and very few of them get addressed. And it's possibly because maybe these people don't care about some of these bugs, but maybe they don't trust how these bugs are generated. So that's a different kind of software engineering issue.
Thank you. I think we need to stop with the questions. So I would like to ask the participants to please continue discussions on the Slack and also in the break on Disco. And with that, I would like to thank Rajeev for his talk and for answering the numerous questions on Slido. Thank you so much.
Thank you.
And I would now like to welcome I would like to welcome our second speaker, who is Rupak Majumdar. He's a scientific director at the Max Planck Institute for Software Systems, and his research interests are in the algorithmic formal verification methods and cyber physical systems. So he has received many awards and recognitions for his research, including most influential papers awards from PLDI and POPL, and many best paper awards. And without further ado, I will now give the floor to Rupak to share his insights about how to do successful research.
Do you need to enable something so I can share my screen?
Let me check.
Yes, you should be able to do it now.
Should be able, yes.
Okay, do you see my slide?
Yes. Yes,
Okay.
and yeah, I would like to ask the participants to use the corresponding link to Slido for questions.
Okay, well, thank you. Thank you, Raina, and the others for your invitation and the introduction. I have to say, when I first received your invitation to give a meta talk, about doing research and not about research, I saw it as a formal obituary to my research career. It's an announcement that that I shall now be talking about doing research and let the younger generation get on with doing research. Also, I was not sure what was expected in a general audience talk on mentorship. So I decided to look up what famous people say about the mentor. And I found a very apt quote by J.K. Rowling, where I only needed to add a few extra spaces. So I think J.K. Rowling really sort of nails the description of a mentor is. And in particular, she says, if it can, the mentor will feed on you long enough to reduce you to something like itself, soulless and evil, which I saw was quite apt. And you will be left with nothing but the worst experiences of your life. So this sounds right, but maybe what I will try to do in the next 40 minutes is not leave you with the worst experiences of your life, but try to tell you a bunch of rules that I found useful. And you should see it with a grain of salt. You should make sure you take what it appeals to you and what doesn't. And the advice I will give you is compiled mostly from others and organized in this talk around aphorisms. And some aphorisms are even pre-Twitter. Okay. So let me start with my background. So I grew up in India, and then I went to the United States to get a PhD. After my PhD, I worked at UCLA as a professor for a few years. And then for the last 10 years, I have been at this Max Planck Institute for Software Systems in Kaiserslautern in Germany. So my research interests are in CAV, in more broadly in programming languages and software engineering research, also in embedded and cyber-physical systems, and also theoretical computer science. Now, my talk will be at a general level, although every once in a while I will probably refer to certain problems or certain papers in our area. And of course, it will be colored very heavily by the kind of work that I like to do and the kind of papers I like to read and write. Right. So I guess it's customary for a YouTube streamer to ask you at this point to hit the like button and subscribe. But instead, I will ask you to do some online homework. What I would all of you to do, if you're listening to the talk, is first, you should write down what you expect to get out of a talk like this. And second, maybe you can also write down one piece of advice that you have found helpful in your research career so far. And you can write this in the, in the Slido or the Slack. And I think this will give us a basis for some discussion after the talk or in the later social discussion hours. And for those of you who get nothing out of this talk, at least you will get a bunch of good advice from your peers. Right. Before discussing how to do research, let's start with the question, why do research? And let's start with some wrong answers. You want to do research because you want to get rich and famous. You want to have a long and prestigious publication list. You want to impress your neighbor. You want to impress your in-laws. Your older brother will finally respect you. And all of these are wrong reasons to do research. But a good reason is that you're excited about an idea and you want to figure out how something really works. So I use here the word conceit. So conceit has two meanings. The usual meaning is arrogance, but there's a secondary meaning, which is a fanciful idea, an organizing theme or concept. So it's really an idea coming together. And I think in research, there is a lot of scientific conceit in this style, and also the optimism that you will be the first person to actually figure out how something works. And this kind of scientific conceit is good. Of course, personal conceit of the other kind, arrogance, is bad. But in some sense, when you're embarking on research, you should think of someone who's embarking on a quest. So what do I mean by quest? So it turns out that quest is something that's a common pattern in a lot of literature. And this is a direct quotation from a book by Thomas Foster. And essentially, a quest consists of 5 things: a protagonist, a place to go, and a stated reason to go there. And then there will be challenges and trials on the way. And then, of course, there is an ultimate, a real reason to go there. Now, in many works of literature, you see this pattern. So from Lord of the Rings to Star Wars to Ulysses to The Old Man and the Sea, there is a protagonist who needs to go somewhere and do something, and there are a lot of challenges, and the story evolves around these challenges. Now, in many of these books as well, you see that, or these stories, you see that the quester can often fail at the task that they set out to do. So why do they do, why do they go, and why do we care? And the reason, as Thomas Foster points out, is that the real reason for a quest is always self-knowledge. We like to see the characters, the protagonists, go through the quest, even though they might ultimately fail, because we know eventually that their quest is educational. And in a way, I think this is very true of science as well. The real reason why we do research, the real reason why we try to solve problems, is really about self-knowledge. It's really about the pleasure of finding things out. Okay, So we see research as a way to self-knowledge. And as a contrapositive, it should not be your main goal to get into research for the glamour or for immortality. Now, this should not be your primary motivators. It can be a byproduct of your work, but usually immortality is outside your control. So if it happens, great. If not, if you focus on producing good ideas, then perhaps the rest will take care of themselves. On the other hand, of course, it is not to say that you're always going into a quest for only your own understanding. It is worth thinking about why certain problems are important, why certain researchers are famous, how does a certain institution earn its prestige. It's just that when we do research, the goal should not be, external esteem, but about the pleasure of finding things out. Okay, so now let's move to the main body of the talk, how to do research. And it turns out that there is a very simple algorithm that that tells you how to do good research. And this algorithm was, as far as I know, articulated by a very famous physicist called Murray Gell-Mann from Caltech. And he was describing how his colleague Richard Feynman does research. And here's a secret algorithm that nobody wants you to know. This is really good, so pay attention, how to do good research. Here's the Feynman algorithm. You write down the problem, step 1. Step 2, you think very hard. And step 3, you write down the solution. And that's all there is to it. No other secret. Now, incidentally, for the venture capital startup types in the audience or the South Park fans, I should say that the physicists figured out this usual way of making money in a startup, right? So you have an idea, then there is some vague intermediate part, everything leading to profit. Right, but let us see how to dissect this Feynman algorithm a little bit better, right? So of course, I'm being a little bit facetious that, this is the way to do research, but there is a grain of truth in it. And I think what I would like to do for the rest of the talk is to go through each of these 3 steps and try to come up with some rules of thumb that tell you, how to do each of these steps. Of course, I'm not going to get you any answers. This is more like collecting the thoughts of other people who have in their own way talked about these 3 phases of doing research. Okay, so the first step is writing down the problem. And as you do more and more research, you realize that identifying what it is you're trying to do is really a crucial first step. And it is more or less as important as the rest of the process. So I'm quoting here the mathematician Cedric Villani in the context of mathematics, but I think this principle of figuring out what to solve is really a hallmark of good science across different disciplines. In particular, I think that this separates the really great scientists from the good ones. The great scientists know not just what are the hard problems, but what are also the problems that are worth solving. Now, there's a very famous speech by Richard Hamming where he talks at length about this kind of problem selection. It's a speech called You and Your Research. And if you haven't read this, I would very strongly advise that you look for it on the web and try to read this essay. And it has a lot of very good advice for beginning scientists. But one of the things he says there is that, well, if you do not work on an important problem, it's unlikely you'll do important work. So, he makes a point that it's not enough just to be working on problems. You should really be working on the important problems, the problems that transform the field. I should tell you that there is not everything in Hamming's article that I agree with. So when you read it, you should also try to take the things that work for you and not everything that he says. But maybe here, I'll tell you an anecdote that Hamming describes in this essay. So he was working at Bell Labs, the same place Rajeev said he used to work at. And at the Bell Labs cafeteria, Hamming would find tables of other researchers and have lunch with them. with them. And he tells us an anecdote that he would sit with some researchers and he'd say, well, what are the important problems in your field? And then he would also ask them, well, what problems are you working on? And if the answers were not the same, he would get feisty. He would say, oh, well, if you're not you're not doing something that's important and you don't think it will lead to something important, why is Bell Labs paying you or some such thing? And as you can imagine, after this, he was usually not welcome at the table anymore. I think this may have been the origin of the term Hamming distance. But the point that he's trying to make is this notion of importance. So this is kind of crucial. But let me also point out a counterpoint. I think it's not a good idea in research to obsess about importance as the only measure of problem selection. I think it's quite easy for us to write down some important problems. Is P equal to NP? Or, is Shanwell's conjecture in number theory true? And so on. But it is not enough just to write down an important problem, because most important problems do not get solved ab nihilo, right? So you need to have a certain preparation in order to be tackling the important problems. So in some sense, the important problems are only recognized a posteriori. With the knowledge of, with the experience and with hindsight, we recognize that a class of problems together make a breakthrough in a field. And in retrospect, we see how these pieces fit together. But in some sense, you cannot really bank your research career on writing down important problems and hoping that you can solve them without much preparation. In order to solve an important problem, you have to be ready. You have to have an angle of attack. You have to have a repertoire of tools. You have to have an understanding of what is hard. And you have to have an understanding of the limitations of your current tools. So I think in some sense, a better advice is what I read once from the mathematician Terry Tao. So he said that it's probably better not to obsess about this one big problem and a breakthrough, but to continually aim just above your current range. So let me call this the AlphaGo principle. So you see these automatic or these machine learned strategies for playing chess and Go and so on. Improve in a certain style where these machine learned components keep playing against their previous versions. Right? So in some sense, they're always being challenged not by completely difficult players or players at a completely higher level, but those that are slight or at or just slightly above the level they are at. So in looking at problems, I can tell you one trick that works for me. Whenever I start writing down a somewhat hard problem, I always look for an easier problem that's sitting inside that hard problem that is still of interest and that I still cannot solve using existing tools. Often, a hard unsolved problem has an easier unsolved problem within it. And that easier unsolved problem may have yet another and still easier problem within that, and so on. So what I found to be interesting in my personal choice of research problems is to identify these sort of simpler problems that are still worth solving. In fact, there is an interesting letter, again from Richard Feynman, where he points out that no problem is too small or too trivial if we can really do something about it. So the worthwhile problems, he says, are the ones where you can really solve or help solve, the ones you can really contribute something to. So a problem is grand if it lies before us unsolved, and we see some way for us to make headway into it. So let me make another point in this same context. Often the importance of a problem is somewhat subjective. So there is a common pitfall of organizing research around only a very specific set of criteria that constitute importance. For example, broader impact to society or industrial impact and so on. While this is often a good idea to select problems that are useful to others and not just internally to the scientist, this can also have certain negative impacts. So for example, in computer science, I think we still have some kind of a post-technical hangover where we were a technical appendage to the real scientists and not a science of our own in our own right. So I think that sometimes we are probably thinking too much on, well, whatever we are working on has to have an industrial justification. But as a science, we should also think about problems that we work because it advances the state of our understanding. And one should not disregard this in the choice of picking problems. So for example, importance, as I said, could be measured in many different ways. There is practical impact, but there is also elegance or depth of theory or a new insight or a technique that has a lot of reuse or a technique that has expository value or it has a pedagogical element and so on. So when you pick problems, it is nice to pick important problems, but one has to realize that importance is not just one absolute metric that you can that everybody can agree on and rank problems according to importance. So one heuristic I often use is what I call astonishment. So good science in some way is like a good sitcom. In a good situational comedy, the best jokes correspond to certain unexpected juxtaposition of events and a coincidence of facts that together somehow become surprising. And in a way, a good research paper or a good research problem is also this way, right? So it puts insights that you may or may not have had before, and it takes insights that you may or may not have before, and then puts them in some unexpected light. Of course, sometimes you build certain jokes from scratch, you build certain techniques from scratch. But overall, a good paper or a good research problem has at the core a certain notion of astonishment or amusement. Now, let me dually point out that it's also sometimes quite easy to convince ourselves that all the problems that we work on are the important problems. And it is actually quite easy to convince ourselves that whatever we are doing is really important. Now, this is where you yourself have to make the call. I think nobody else can really make it for you. Are you picking the problems because you're comfortable with the techniques and you have written 1,000 other papers that are just like it? Or do you think of this as a quest? Do you really think that you're going to work on something that, if nothing, will lead to a certain self-knowledge? Okay, let's now move to step 2, thinking very hard. And let's first get the elephant in the room out of the way. So if you just write somebody else's thoughts into a blog post, that's probably not the kind of thinking that I'm thinking about. Now, unfortunately, there is really no royal road here. There is no easy way that I can tell you that do this and you are thinking hard. There is no royal road to geometry, as Euclid said a long time ago. So you have to put in the effort. Now, every once in a while, it is possible that sheer luck leads you to a problem, to the solution of a problem. You can be completely unprepared, and yet you might be able to come up with a really great solution by yourself. But what I would suggest is do not bank your career on doing this. Now, as Louis Pasteur said a long time ago, fortune favors the prepared mind. So often when you consider someone who has this luck, often you say that, look, this person is so lucky that they came across these ideas. You will notice that the luck is really a byproduct of a lot of hard work and a lot of experience that goes into thinking about these problems. And this doesn't happen without the effort. In fact, you can rely on your intelligence and quick thinking, for a long time, and maybe this works for you for a while. But in my experience, and I think in the experience of many others, eventually it doesn't. Eventually, between the person who is intelligent and puts in hard work and the person who is really only intelligent, the person who puts in hard work usually wins. In fact, again, Terry Tao has this essay where he talks about how math came to him very easily. And of course, he's a very intelligent person. And yet, because he didn't put in the hard work, he almost failed out of grad school because he was going to fail his qualifying exam. And so this, he said, was a turning point in his career where he realized that it wasn't enough to just be smart. You also have to put in this hard work. And again, we like the cult of genius, the outside loner coming in, hacking for 10 minutes and getting this eureka moment. But unfortunately, outside of Hollywood, such moments are largely a product of hard work and experience and intuition. Now, the other point is that, working hard also means that you have to constantly renew yourself. So again, Feynman had this thing where he said that his mode of doing research was always to keep a number of open problems in the back of his mind, and also to keep a number of techniques. So whenever he would learn a new technique, he would go and try to apply it to one of the problems he had and see if one of them would be able to, whether he would be able to make progress on one of them using the new technique. And conversely, whenever he saw a new open problem, he would go through his list of techniques to see if one of them worked. Now, whenever he, in this way, he said that, well, he was able to make a lot of progress on a lot of problems that people thought were really unsolvable. Now, it is crucial in this process to keep learning new techniques, and also to understand the limitation of your current techniques. If the only tool you have a hammer, then everything will start looking like a nail, and you will only be able to solve those problems that really require a hammer. And the other interesting point that you will notice after doing research for some time is the interconnectedness of ideas. Often a research problem is solved because people are able to see this problem from various different vantage points. So when we are at school or at college, we learn these, a certain set of topics in these silos called courses. But as you do more research, at some point you realize that the line between these different courses or these different topics get blurred. At some point, you see that a certain problem really requires you to understand various different techniques from various different disciplines in order to be able to say anything new or meaningful. So, for example, in our field, if you think about the transition from understanding how philosophers talk about discourse that refers to time to automatic tools that look at the correctness of hardware or software systems, you see this kind of blurring of boundaries. So temporal logic, has its roots in philosophy, and it is used in a very algorithmic style in verification. And it's also similar, when we think about logic in general. On the one hand, we study logic to understand the foundations of mathematics, and on the other hand, we study logic using as an algorithmic basis to deal with deduction. And this is nothing new, if you go back to Leonardo da Vinci, he has this saying where he says that you have to study the science of art and you have to study the art of science. And you have to realize that everything connects to everything else. And in some sense, this globalization, in computer science, it's often summarized as good theory requires good practice and vice versa. So it's not really enough to be saying that, well, I will learn this one technique that comes out of my field. Sometimes you have to be a little bit broad and understand how different techniques connect with each other. I think there is some aphorism that mathematics is a way of giving the same name to different objects. And there are these very wide-spanning programs in mathematics, like the Langlands program, that try to put two different fields together. But this goes back to this comment about the interconnectedness of ideas. Actually, there's a very interesting essay by Umberto Eco, where he talks about the influence of one writer on the writing of another. And Umberto Eco draws this triangle. He says that, well, there is the writer A and the writer B, but there is a third vertex in all this, which he calls culture or the background. And his point is that, well, the influence between authors or between ideas really also depends on this third, the background or the culture of ideas. So the way you can think of this triangle is that, well, the relation between A and B can take place in different ways. So for example, B finds something in the work of A, but does not realize that behind it lies the culture, the X. Or B finds something in the work of A and through it understands how it relates to the culture X. Or B directly refers to the culture or the background and only later realizes the way X was reified in the work of A. So in literature, I think there is a term called intertextuality, which essentially means that a piece of text can be shaped in its meaning by another text. So for example, there are retellings of stories that have been told before. For example, West Side Story is a retelling of Romeo and Juliet. Ulysses is a retelling of Homer's Odyssey, and so on. And I think both of these, Eco's triangle and this notion of intertextuality is also there in this interconnectedness of science. So in some sense, you can think of the story of science as really one big story. And then there are smaller stories that we grow that come as offshoots to this one big story. And these stories are the ones that we retell in a different way, in a different context. So often you see that, and in all of this, the role of background knowledge has to be acknowledged. I mean, in some sense, it's quite surprising how often you will see that there is this long-standing open problem for a long time, and then suddenly somehow several people independently come up with a solution to this problem. So in some sense, this is Eco's influence of X, influence of culture. And in a way, this kind of intertextuality is, shows up in the sciences because we look at different ideas, we combine these ideas in new ways, and we take certain stories that have been said before and we retell them in a different context. So,
Rupak,
yes.
Can I interrupt with a couple of questions from Slido?
Yes, please.
Thank you. So one of the questions is if you could explain via some example, what do you mean by technique? So more concretely.
Yes, so, I will talk about a particular thing that I'm working on now, right? So I'm looking at certain problems in dynamical systems and control. So this goes back to what Rajeev was talking about in the analysis of cyber-physical systems, right? We would like to show that a certain cyber-physical system satisfies a certain property. Now, this is the overt problem. Now, if you think about it, the techniques to solve this problem come from two different disciplines. It comes from control theory, the study of dynamical systems. And traditionally, control theory is about continuous mathematics. The techniques come from analysis and topology. And on the other side, we are interested in the algorithmic questions. We would like to have algorithmic solutions to things that take dynamical systems and reason about them. And here the techniques come from logic and algorithms and other things in computer science. So in order to solve these problems, we have to somehow put these together. We have to somehow see how dynamics interacts with computation. So this is what I mean by technique. So these techniques are, well, we know things about decision procedures. We know how to encode certain things in certain logics and have a general algorithm to solve them. On the other hand, we have techniques from analysis that tells us that we can give certain properties of the system that we can infer through techniques of continuous mathematics. And now there is a question of putting them together. And in putting them together, you may have to come up with relating these two things in a way that nobody did before. So does that answer your question? Or, I mean, we can go offline and I can give other examples as well.
Thank you. Maybe one more question. So on top of Slido, there is a question that asks about competition between researchers and scooping, and then how would one deal?
We'll come back to this at the end.
Okay, thank you.
Okay, let's hold that thought for the moment.
Thank you.
So one thing I should say is that, it might seem really daunting that, oh, you have to learn all of this and not just your field, but every other field. And somehow you have to make all these connections. And as a beginning researcher, it might seem really overwhelming. How do you do it? And I think the simplest way to approach it is that, first of all, you have to understand that, slowly, so, okay, this is part of the thing that I wanted to say, but okay, slowly, that you're not alone in all of this, right? So usually science is a social activity, and we work with other scientists when we think about these problems. So you are working in the community of other scientists, and what you should really do is ask them questions. So of course, you cannot ask Feynman all the questions you have, but the point I'm making here is that when you have a difficult problem, one way of making progress there is to find people who have expertise in certain aspects and just try to get their knowledge. So good science often progresses through a combination of effort, right? So find collaborators who have complementary strengths. Find someone who really understands some aspect of the problem. Find someone who can really formulate new theoretical principles. Find someone who is really good at problem solving. And ask them questions. Usually at the beginning, we are always worried that we are going to be asking the dumb questions. But I think this is really not something to be worried about. And conversely, you will have other scientists who come to you about questions, right? So you will slowly build up a set of tools that you know, and then you can help and answer questions from other people as well. So, and I guess, no talk in computer science is complete without an aphorism from Dijkstra. And Dijkstra said this very interesting thing, that is, do only what only you can do. In some sense, find out what is your unique perspective to doing research. And this is where you are probably going to solve the best problems. Right. So let me now come to the third part. So, well, maybe before that, I can give you, again, a very concrete example. There's a story that when John Nash was working on some, very difficult problem, the embedding theorem, he kind of started by knowing very little about the subject. But then he found a lot of people and he kept asking them a lot of questions. And slowly, piece by piece, he kind of put together and he sort of distilled the idea of all of these different people into solving, into proving this theorem. And there are many other examples from our own field where, a team of scientists with complementary skills really makes a breakthrough on a problem. Okay, so now let's come to the third part, writing down the solution. Now, one should not underestimate the value of clearly communicating an idea or a result. It is often not sufficient just to find a solution. You need to communicate the solution clearly to other scientists and perhaps to other people beyond your colleagues in your field. And usually a clearly communicated lesser idea can outplay a badly communicated but really good idea. So one has to really take the time to communicating or to writing down the solution in the best way. Now, there is a lot of saying, advice about good writing, and I certainly do not want to get into how you write well in the rest of the talk. For example, you can see Ranjit's talk later in the workshop about clear communication, but you can also find online many other sources of very good advice about writing. One thing I will say, though, is that in addition to reading, these kinds of advice on scientific writing, one thing that I find very useful is to read good literature. On the one hand, you can get all the abstract principles of good mathematical writing from many of these books on writing, but there is no greater pleasure of really reading a good piece of literature and seeing how the author is making the case. How the author is weaving all the sentences that want you to read more, want you to know more what happened. So read Hemingway, read T.S. Eliot, see how their stories fit together, see how their poems fit together, see how each line is somehow bringing you, getting you to read the next one, and so on. I would probably recommend not reading Joyce, especially not reading Finnegan's Wake at this point. But you see what I'm trying to get at. I think there is a lot of value in just reading good material from really good writers beyond your discipline. It's, literature is one obvious place, but you can also read a really good essay on philosophy or something else that is not about computer science, but that can get you an idea of how to communicate ideas clearly. Okay. Now, at this point, I should talk a little bit about external influences. Now, unfortunately, this is a part of academic life. Your best ideas, even when communicated perfectly, can still be rejected. And rejection is in two parts. There is internal rejection and external rejection. Now, you see, internal rejection is what I call because you as a scientist should be the worst critic of your own ideas. So there is a duality in the way we work, right? On the one hand, we really believe in these ideas that we have. We are really optimistic that they lead to something new. And when we are trying to solve a problem, this optimism is really crucial. You have to believe that what you have is a way to solving the problem. But at the same time, once you have solved a problem, you have to be your worst critic. You have to find all the possible ways you can poke holes into the argument that you have just built. Because if you don't, somebody else will. So this is what I call internal rejection. You should be able to reject what you have spent a lot of time developing, just because all your ideas may not be good. And in some sense, it's very easy to convince oneself, especially when you have put in the effort of months behind an idea, to be convinced that this must be a good idea. External rejection is what I call what happens when you submit an idea for review to the community and you get back possibly unfair comments where people do not like this. Now, I should also mention that when you have a genuinely creative idea, this is very likely to be met with rejection. Because very creative new ideas necessarily threaten the way we think about a topic. And something that is really novel causes some discomfort to us. So, as humans, we have very, two opposite qualities biasing our minds. We have habits, things that we are used to, and novelty, something new. And I can tell you that 90% of the time, when confronted with habit over novelty, we tend to pick habit because we are just more comfortable. Novelty requires us to change the way we think, to change our wealth build. And this requires more work. So, as you write these papers, as you write new research results, you will see often that, well, they get rejected. And this can be quite devastating, So dealing with failure or rejection turns out to be a part of a research life. And one has to understand that rejection of an idea is not a rejection of you. I mean, it feels really bad, even now when I see a rejected paper, I'm not in a good mood that day, I'm really grumpy. On the other hand, if you're not occasionally failing in your research, perhaps you're not being ambitious enough. If every problem that you start out with gets solved very quickly, maybe you should be looking at harder problems. And similarly, perhaps if you're not occasionally rejected, you are preaching to the choir. I think there is a lot of emphasis we place on novelty, but we're really uncomfortable when we see novelty. And this is something that you have to learn to live with. And this is not just me telling you because I get a lot of rejections. It's true, I get a lot of rejections, but here's what Blaise Pascal said a long time ago. He said, do not say I have said nothing new, because the arrangement of the subject matter is new. I wish I could start every rebuttal this way. Okay, but at the same time, you have to make sure that you're not convincing yourself that you're using really novel work, because really when you're doing work that's not so great. there is a statement that I saw on Twitter that resonated with me. So it said, to test if your paper makes a genuine contribution to its discipline, see if you can afford a generous tone in the related work section. If you're really being mean to other papers in order to make your point that previous work required 17 assumptions and your work requires only 16, perhaps you are not as novel as you think. And similarly, if you are getting reviews that look like this, perhaps, again, you need to think through whether you're looking at the right class of problems. Now, there's an excellent essay by T.S. Eliot where he talks about new works of art coming into the world of the existing art. And he makes this analogy that the world of art is kind of a sequence, a number of monuments that fit together in a certain way. And in some sense, they fit together perfectly in some kind of ideal order amongst themselves. Now, when a new piece of art comes in, it kind of finds its place in this set of all monuments. And the entire order, which was complete before, gets reshuffled or slightly altered so that the new idea fits in. And after it fits in and the whole thing is readjusted, we have again a world of art that is in an ideal order among themselves. In some sense, good research ideas are like this. We are building up on a lot of existing research ideas, and we are somehow coming up with something new that still has a connection to everything that came before. And when these new ideas come in, the entire structure of science is altered ever so slightly. So there is a poem that I saw actually just yesterday that I thought made this point in a very nice and eloquent way, about new ideas expanding the horizon. And I think there is something beautiful in doing good research. Now, I want to come back to the question that came up before, and I want to spend a little bit of time talking about how not to do research. So you know that in learning theory, we know that it's really important to have negative examples as well as positive examples. And so let me just go over quickly a few things that are, that you should be mindful of. So the first thing is that you really should distinguish between form and content. So, a good paper is ultimately a paper that introduces a new idea, one that makes you think. And as I said before, this idea, this notion of importance can be subjective and can span across various different subjective domains, but there has to be a new idea. It's not enough to just have a clear plastic binder. The second one is, you should really aim to publish your best work. It's not necessary to publish all your work. So this is again, something that Leslie Lamport quoted. I'm not sure who this quote is from. That says, judge an artist not by the quality of what is framed and hanging on the walls, but by the quality of what's in the wastebasket. Now, the other point that you have to understand is that sometimes good ideas will take some time to be accepted. So this is what Max Planck said, science advances one funeral at a time. The old guard will slowly move away, leaving room for the new ideas to get prominence. So you have to understand that sometimes bad ideas can keep good ideas out. And I think the fourth point and more general point is that you have to approach your scientific work with honesty. So this is a very famous editorial that Claude Shannon wrote in 1956. Again, I don't think you have to read it now, but I would highly recommend reading this offline. And Shannon wrote this in the context of information theory. And he was pointing out that there is a danger of overhyping a technical area and to contend that this overselling and peripheral attempts to solve hard problems in different areas without really understanding the problems of these other areas can be detrimental to a field. I think this is actually a very good read, and these points that he made so many years ago are still very true. You might think, of course, that, in our field in computer science and in these enlightened times, such bandwagonness or such drumming up hype will never, ever happen. right? Right? Okay, so now I come to the last and perhaps most important slide in this talk. Now, the world of science and research mirrors the more general society among us. So there is the scientific work that we like to do, but at every point we have to understand what is the consequence of what we do on the rest of society. We have to ask the question whether what we are working on is ethical, is really beneficial for society as a whole. Now, there is a second point. Unfortunately, society has a fair share of people who are just not nice. So, and science is sort of a microcosm. It's a mirror of society, and you can believe me when I say that there are people in our community who are also perhaps not so nice. So this gets back to this competition among scientists and scooping ideas and so on. I think competition in the sense that I would like to be the first person to understand something is a good thing. This is what sort of drives up to find good results. On the other hand, one has to somehow step back and take the bigger picture. I think we are all sort of fitting in, these small stories that the entire story of science is about. And it can be really bad if in some sense we tend to certain dishonest means, certain intellectual or behavioral dishonesties in dealing with other people. I think it can be quite devastating to, if you come across bad behavior, and I'm sure that some of you have at least come across certain behavior that was questionable. And in some sense, it is very difficult for us to not react negatively to bad behavior. For example, if you see that you got a bad review, quite unfair review on one of these papers, it is very difficult to say that I will not give a harsh review to the next paper that I review. But I think in some sense, at least in an ideal setting, it is really important for us that we aim for our best behaviors. Not just our best scientific results, but also our best ways to interact with the rest with the community of scientists. Look, we are all part of this very wonderful community of scientists. We're together telling the most fascinating story in the intellectual history of the universe. And I think it's really important that we keep our community healthy and vibrant. So if you just remember one piece of advice from this entire talk, it's don't be a jerk. Thank you for your attention, and I'll be happy to take more questions. And I would also like to see the kind of advice that you've written in the chats channels during my talk. Thank you very much.
Thank you very much, Rupak, for this insightful talk. We have a good time for questions, and there are a couple of questions already on Slido. So the question that is currently on top is, I think it's quite an important one, and it's namely how to determine whether to move on from a failed project or approach, how to identify the point when you have to move on.
Yes. Richard Lipton calls this a mathematical disease, when you're working on a problem and at some point it becomes an obsession and you just keep at it without making progress. And many of us have had this. I don't know if there is a standard answer to this. I think it really depends on you. One thing that I often do is not just work on one problem. Think of this Feynman list of learning techniques and applying them to problems. If you're not just working on one problem, but also at the same time reinventing yourself by learning new techniques, perhaps this process of learning takes you to new problems and helps you move on. I don't think there is really a quantitative sense in which you can say work on it for 3 months and so on. I think Jeff Ullman has this quote where he says, never work on anything for more than a year. On the other hand, there are some famous examples of people working for multiple years and solving a major open problem. Fermat's last theorem is one of them. So really, it depends on you. It depends on whether the skills that you're gaining while trying to solve this problem are transferable. Whether you are learning something that even if you were not to be able to solve this current problem would be useful to you somewhere else.
Thank you. There is another related question, which is, what to do when if you find out that the problem that you have been working on for a long time is no longer important. I guess it's the same.
Well, yes. I mean, sometimes this can happen. On the other hand, never underestimate what you have learned in a project. So at some point, once you have learned something well, there are always other problems that are situated somewhat close to it that may still be important. It's a related question. What happens if you worked on something for some years, you solved it, but somebody solves it just before you do? And this can happen. And in a way, often you will see that even though people are solving the same problems, the actual paths to the solution are different. In this case, you can show people a different way of solving the same problem. And there's often quite a bit of value in that, because there may be a different insight that came through your solution. Sometimes it can also happen that, you solve it in exactly the same way. And it is perfectly fine to, use this as an experience. You learned something, move on to a different problem. It's important to get good ideas, and sometimes it just happens that somebody else beats you to it. But in the long run, sometimes you will beat somebody else. It's over time. You win some, you lose some.
Thank you. We have one question, which is how to, if you have any tips, how to overcome the fear that perhaps the question that one is asking is not kind of, it's not the most interesting question, or it's a dumb question.
Yeah, I don't know. I mean, this is where, some experience helps. So in some sense, it's not like you get into a graduate program and on the first day, your advisor says, so you got any good questions? So, it's a matter of, reading, understanding the literature and talking with others. This is essentially why in grad school, most places insist that you have an advisor. The role of the advisor is often not to solve your problems for you, but essentially to develop this taste in you about what questions are important and what is not. In some sense, the goal of the PhD is not to solve a specific set of problems, because in some sense later on you might very well be working on very different topics, but to develop this taste for a topic, to develop this taste for a subject and be able to distinguish what are the good questions and from what are the not so good questions.
Yeah, I think that's related to another question that we have, which is how to make the case for a chosen problem. So the argument, the question states that it's like motivating a sub-problem of a bigger problem is challenging, right? How do you kind of justify that the sub-problem is interesting on its own?
So often some of these sub-problems may not be interesting, but they aid in preparation. When you build a skyscraper, you don't start building a skyscraper. You may start by building a clay model of a little hut. Now, maybe this particular hut is not interesting to anybody. On the other hand, this gives you an understanding of the tools that you need and the problems you might face in solving the bigger problem. So one shouldn't really think about this as, what is the economic output of every small problem that you look at, of every simplification. Think of some of the simplification as the cost of doing business. You want to solve a difficult problem. First, you have to solve a few simpler ones. And even if these simpler problems do not by themselves have any interest or importance to them, this is essentially telling you how you can make progress on the more difficult problem.
Thank you. And I think we have time for one more question. If you could name a couple of forums where one could ask questions from the formal verification community.
I don't understand. This is like something like Stack Overflow or?
I mean, I guess, yeah. I mean,
so in the types world, and there are some mailing lists, although I guess mailing lists are not so cool anymore. But then, there's a types list and there's a concurrency list where often some technical questions get discussed. You would be surprised how many experts will reply to you if you pose an interesting and thoughtful question on Twitter. You will be surprised how many people take time off to answer very detailed, give very detailed answers to questions on sites like Stack Overflow. So, I mean, these are the obvious ones that keep spring to mind. But of course, you can also, if you have a thoughtful question that you want to ask a researcher, you can always send them email, and don't be discouraged if, if they don't reply back immediately, because, we are all very busy, we have many other things to do and so on. But it is possible that someone will understand and like your question, and they will get back to you with a thoughtful answer.
Okay, thank you. I think we can move on to the break now. So thank you once again for the talks and for answering all the questions to both speakers. And yes, I hope you all join us on Disco for the break, where we can continue the discussion. There are a couple of leftover questions on the Slido. We will move them to the Slack, or then they can also be the basis for discussion at the Disco group meetings at the break. Thank you.
Thank you.